On May 11, 2026, Sunspot region AR4436 released an M5-8 class solar flare, a blast of electromagnetic energy that crossed 93 million miles of empty space and slammed into Earth's ionosphere at the speed of light, triggering an R2-level radio blackout that instantly severed high-frequency communications. Across the entire continent of Eastern Africa, that blackout did not last an hour, it did not last a day. What matters is what it announced. AR4436 is now rotating into direct Earth-facing alignment, and NOAA's Space Weather Prediction Center and the UK Met Office have both confirmed that a coronal mass ejection from that same event may deliver a glancing blow to our planet's magnetosphere as early as May 13, 2026. 2 days from this moment, if you rely on this channel for science that is grounded in verified data and explained with honesty, subscribing ensures that none of this reaches you late. This work depends on the audience that values it. The instruments are showing this in real time, and the story it tells deserves to reach every person who needs to understand it before the next event arrives. Every figure in this script was drawn from official scientific and governmental sources: NOAA's Space Weather Prediction Center, NASA's Solar Dynamics Observatory, the European Space Agency's SOHO spacecraft, the South African National Space Agency, EarthSky's Solar Reporting Team, and peer-reviewed space weather research published in the journal Space Weather. But official sources are not infallible, and neither is the human process of reading them. Before any decision is made, whether personal, professional, or otherwise, verify independently through the official channels. The sources are listed, the data is public, the responsibility to check belongs to all of us, but that is not even the complete picture. What you have just been told describes a single flare from a single sunspot rotating into view. What the official data actually shows is something far larger, far older, and far more consequential than a radio blackout over Eastern Africa. AR4436 is not a freak event. It is not an anomaly. It is a single, relatively mid-sized actor inside a solar system that is currently operating at or near the extended peak of solar cycle 25, a cycle that was predicted by an international panel of scientists convened by NOAA and NASA to reach a maximum smooth sunspot number of 115, and that instead has already produced an observed smooth sunspot number of 157, measured in August 2024, sitting entirely outside the boundaries of what the official consensus forecast said was possible. The sun overperformed every model that was supposed to contain it, and it has not stopped. The early months of 2026 have continued the pattern. On February 1st and 2 of this year alone, a single hyperactive sunspot region designated AR4366 unleashed at least 18 meters class flares and 3X class flares within 24 hours, including an X8-3 eruption that stood as the strongest solar flare of 2026 at the time it occurred. That was 3 months ago. The sun has not rested. And now AR4436 is rising in the east of the solar disk, rotating steadily toward the position where everything it fires will be aimed, at least partially, at us. Here is where this account becomes genuinely significant. The M5-8 flare that AR4436 produced on May 10th was not its first demonstration. The region has already drawn the attention of every major solar monitoring body currently operating. SpaceWeather's community tracking page shows AR4436 generating substantial discussion even before its current transit, with observers noting a coronal wave and shockwave visible simultaneously in the 300 angstrom wavelength at the time of the main eruption, a signature that solar physicists note as particularly significant because it suggests the energy release was not confined to a narrow magnetic loop but propagated outward across a wider portion of the solar atmosphere. The CME that followed appeared at 1348 UTC on May 10th in the SOHO spacecraft's LASCO-C to coronagraph imagery, a significant partial halo CME, which means the ejected plasma cloud was large enough to appear as a partial ring around the sun in the coronagraph's field of view. The bulk of that ejecta was directed east of Earth. But initial modeling from the CNLIL Solar Wind Prediction System, the primary computational tool used by NOAA's Space Weather Prediction Center to forecast CME trajectories, points toward a possible glancing blow arriving at Earth in the early UTC hours of May 13, 2026, if the Earth-directed component is confirmed. By updated modeling, forecasters have estimated that the KP geomagnetic index could reach 5, placing this event at G1, a minor geomagnetic storm by the official scale. Significant uncertainty remains in those numbers. But the more important fact is the one sitting directly behind them. A 5% chance of an isolated X-class flare also remains, according to current NOAA forecasting, generated by the combination of AR4436 and its companion region AR4432, which has independently produced 8 C-class flares and 1 B-class event in the same observation window. 5% sounds small. 5% is not small. 5% is the probability that the most energetic class of solar explosion that the sun can produce happens in the next 24 hours from a source rotating directly into Earth's strike zone. When solar physicists use the phrase strike zone, they are choosing their language carefully. That careful language is itself the warning. Think for a moment about what a radio blackout over Eastern Africa actually means, not as a data point on a monitoring screen, but as a human experience. The R2 classification means moderate disruption to high-frequency radio communications. High-frequency radio is not an antiquated technology relegated to shortwave enthusiasts with vintage equipment. It is the backbone of aviation communications across oceanic routes where satellites have gaps, the primary communication system. For remote medical facilities in parts of eastern Africa where ground infrastructure does not exist, and a critical fallback layer for maritime navigation in the Indian Ocean. When AR4436 fired at 1319 UTC on May 10th, pilots crossing the Indian Ocean and the Eastern African airspace on high-frequency communication systems experienced degraded or severed contact with ground controllers. That degradation lasted for the duration of the flare. The flare itself ran for 37 minutes. According to monitoring data reported by World Today News, 37 minutes. That is the length of a full approach to landing sequence for a commercial aircraft. That is long enough for a maritime vessel to travel several nautical miles through contested or hazardous waters without reliable position confirmation. The blackout was not catastrophic in this instance, but the question is not whether, the question is when a blackout of this duration and this reach coincides with a moment where it matters most, and that question connects directly to a day that people in the province of Quebec, Canada, still describe with a particular silence. On March 13, 1989, at 2:44 in the morning, Earth's magnetic field was fluctuating with a violence that had not been seen in decades. The fluctuations were the product of two successive coronal mass ejections, the first associated with an X4-5 solar flare on March 10th, the second linked to an M7-3 flare on March 12th. Researchers publishing in the journal SpaceWeather have since documented that the second interplanetary CME shock arrived at a transit speed of approximately 1,320 km per second, more than 4 million km per hour, and that its arrival coincided precisely with a substorm that triggered geomagnetically induced currents, or GICS, in the high-voltage transmission infrastructure of hydro. The province of Quebec sits on the Canadian Shield, a vast ancient formation of crystalline basement rock that does not conduct electrical current efficiently through the ground. When a geomagnetic storm induces electrical currents across the surface, the currents cannot dissipate through the rock beneath. They are forced to find a less resistant path. On March 13, 1989, they found that path through 735,000-volt transmission lines that stretch for hundreds of kilometers across the province. The hydro protection system was triggered. Within 90 seconds of the storm's arrival, the power grid of an entire Canadian province collapsed. 6 million people lost electricity without warning. Darkness descended across Quebec at 2:44 in the morning. It lasted 9 hours for most, and for some, far longer. Auroras blazed across the sky as far south as Florida, Texas, and Cuba. People in the United States, watching strange lights pulse across the winter sky, reportedly feared they were witnessing the opening stages of a Soviet nuclear strike. The Space Shuttle Discovery was in orbit at the time. One of its fuel cell sensors began reporting anomalous pressure readings that could not be explained. The anomaly disappeared when the storm subsided. NASA has never officially linked the sensor malfunction to the solar storm. 200 power grid problems erupted across the continental United States within minutes of the storm's arrival. None of those produced a blackout, not because the grid was immune, but because on that morning in 1989, enough surplus generation capacity existed to absorb the disruption, just barely. This is not a hypothesis. This is documented in the geological record and in the engineering archives. The magnetic index Kp reached 9+, the absolute ceiling of its measurement scale, during the March 1989 event. The DST index, which measures the disturbance in Earth's magnetic field, reached -589 nanoteslas, the largest value recorded since the index began in 1957. And the March 1989 event, extraordinary as it was, is not even the largest solar storm in the record of human civilization. In September 1859, an amateur British astronomer named Richard Carrington observed from his private observatory a peculiar white light eruption on the surface of the Sun, a burst of such intensity that it remained visible even through his telescope's solar filter. Hours later, the storm it produced struck Earth's magnetic field with an estimated DST value ranging, depending on the reconstruction methodology, from -850 to -1,760 nanoteslas. Every telegraph system on Earth was disrupted. Telegraph operators in the United States and Europe reported sparks leaping from their equipment. Some reported receiving electrical shocks. Some telegraph offices caught fire. Operators in some regions found they could continue transmitting messages even after disconnecting their batteries entirely, because the geomagnetically induced currents flowing through the wires were strong enough to power the system without any external source of electricity. The aurora was visible at latitudes as far south as the Caribbean. People in the northeastern United States could read a newspaper outdoors at midnight by its light. The National Academies of Sciences has since estimated that a Carrington-equivalent storm directed at the modern technological infrastructure of the United States alone would cause between $600 billion and $2.6 trillion in damages, with an estimated 20 to 40 million people potentially facing extended power outages lasting anywhere from 16 days to, in the most severe scenarios, 1 to 2 years. This has already happened once. The record of it is still preserved in the magnetogram archives and the scorched relay equipment of the Victorian telegraph system. The question is not whether it can happen again. The question is whether what is accumulating in the magnetic field of AR4436, a sunspot rotating steadily into position on the Sun's northeastern limb on the morning of May 11, 2026, is part of the opening sequence of the answer. Think about the people for whom that question is not abstract. Think about Nairobi, Kenya, a city of approximately 5 4 million people, the largest metropolitan center in East Africa, a hub of aviation, banking, telecommunications, and regional government. Nairobi sits well within the sunlit zone of the hemisphere that faced the sun when AR4436 fired on May 10. The radio blackout that followed touched the communications infrastructure that connects Nairobi's Wilson Airport to regional air traffic control, that connects vessels in the port of Mombasa to maritime coordination services, that connects remote hospitals in the Rift Valley and the Northern Highlands to the medical coordination networks, that route emergency assistance. Those people were not watching a solar monitoring screen. They were doing exactly what they do every morning, making decisions, moving vehicles, treating patients, conducting business inside a communications environment that had just been partially severed by an event 93 million miles away that they had no knowledge of and no warning about, because the R2 radio blackout did not require any public emergency notification under current space weather alert protocols. This is what the data looks like from the inside, not a number on a scale, a morning in Nairobi where the radio system that guides aircraft does not work quite right for 37 minutes, and the reason why is circling the sun on a trajectory that is rotating it closer to Earth's direct line of sight with every passing hour. The system is not inactive, it is accumulating. And here the science connects to something that reaches well beyond the behavior of a single sunspot. AR4436 does not exist in isolation. It is rotating into prominence during a specific phase of solar cycle 25, a cycle that has already exceeded every prediction made by the international scientific panel assembled to model it. The smooth sunspot number that NOAA and NASA predicted as the maximum for this cycle was 115. The observed value reached 157 in August 2024. Solar cycle 25 then entered its official maximum period, declared by NASA and NOAA representatives in October 2024, but the activity did not plateau. It intensified. Through the winter and spring of 2026, sunspot regions have continued to produce major eruptions at a frequency that analysts at Climate Cosmos describe as 40% above baseline X flare frequency compared to what models predicted. The X83 flare of February 2, 2026 was the largest single eruption of the current year at the time, the April 26, 2026 M6. Zero flare from AR4420 prompted NOAA's Space Weather Prediction Center to issue a forecast carrying a 70% probability of additional M-class flares and a 25% probability of X-class flares through April 29. Now, 2 weeks later, AR4436 is producing M5. 8-class eruptions from its position on the northeastern solar limb, still in the process of rotating into the most dangerous position, full Earth-facing alignment, and NOAA's current 45% probability for M-class flares over the next 24 hours is not a number generated by pessimism. It is generated by the observed behavior of a magnetic region that has already demonstrated its willingness to fire. Here is where the connected systems become impossible to ignore. The vulnerability of Earth's power grid infrastructure to geomagnetically induced currents is not uniform. It is shaped by geography, geology, and the physical architecture of the transmission systems themselves. The Canadian Shield, the ancient Precambrian rock formation that underlies Quebec, is one of the most electrically resistive geological formations on Earth, which is precisely why the March 1989 storm hit Quebec with such ferocity. Similar geological conditions exist across Scandinavia, Finland, northern Russia, Alaska, and parts of South Africa and Australia. These are the regions where GICS find the least resistance in the Earth and the most efficient pathway through transmission infrastructure. A 2003 geomagnetic storm associated with the so-called Halloween solar events induced sufficient GICS to damage several power transformers in South Africa, caused a power blackout in the city of Malmö in southern Sweden that left 50,000 people without electricity, and created induced currents in the Finnish natural gas pipeline network. Transformers are not generic industrial components. Large high-voltage power transformers, the kind that sit at the backbone of continental grid infrastructure, cost between $3 and $10 million each and have manufacturing lead times that currently run from 12 to 18 months at major suppliers. There are no large warehouses of spare transformers waiting on shelves. When one burns, the wait for its replacement is measured in months, not days. The sun does not consult infrastructure procurement schedules. Minutes are not hours, and in this context, that difference is everything. The interval between a CME departure from the solar surface and its arrival at Earth averages between 1 and 3 days, depending on the ejection velocity. The fastest CME in the modern instrumental record, associated with the July 23, 2012 solar storm, traveled from the Sun to the orbit of Earth in approximately 18.6 hours. That storm missed Earth by a matter of days in its trajectory. A 2014 study published in Nature Communications estimated the probability that a Carrington-class event would strike Earth in any given decade at approximately 12%. The current decade has not yet ended. Think then about a city like Lahore, Pakistan, a metropolitan area of approximately 14 million people. In the Punjab province, one of the densest urban concentrations in South Asia, sitting in a region where power infrastructure is already operating under significant stress during peak seasonal load periods. Lahore's position in the northern hemisphere places it in a zone of moderate but real GIC vulnerability during major geomagnetic storms, particularly given the long transmission corridors connecting Pakistan's national grid. The people of Lahore are not unfamiliar with power disruption. What they have not faced is power disruption. caused by a geomagnetic storm of the severity that the record says is possible and that the current solar cycle says is not impossible. The question a resident of Lahore might ask, if they had the data now visible to any person monitoring NOAA's Space Weather Prediction Center, is the same question a resident of Quebec City asked in the early hours of March 13, 1989, after they had been sitting in total darkness for 3 hours with no information about when the lights would return, not what happened, but whether anyone saw it coming and chose not to say so in time. The monitoring infrastructure that exists today is incomparably better than what existed in 1989. NASA's Solar Dynamics Observatory watches the sun in multiple wavelengths simultaneously, 24 hours a day, with a resolution and cadence that the instruments of 1989 could not have approached the SOHO spacecraft. A joint project of NASA and the European Space Agency provides continuous coronagraph imagery that makes CMEs visible within minutes of their departure from the solar surface. NOAA's Discover satellite orbits the L1 Lagrange point approximately 1 million miles from Earth, a gravitationally stable position between Earth and the Sun, and provides real-time solar wind data that gives forecasters between 15 and 60 minutes of advance warning before a CME arrives at Earth's magnetosphere. The South African National Space Agency monitors solar activity and its electromagnetic impacts across the African continent. The UK Met Office operates a space weather forecasting centre that issued a formal warning alongside NOAA's regarding the AR4436 CME now in transit. The system is watching. The question is whether what it sees in the next 48 hours will demand more than a watch. What the official data actually shows is this: at 2 UTC on May 11, 2026, the Sun displayed 5 numbered active regions on its visible disk. AR4436 was rising from the northeastern limb. AR4432, which has been the lead flare producer in recent days with 8 confirmed C-class eruptions in a single observation window, sits elsewhere on the disk. The 7 cm radio flux, a standard measure of solar activity used by NOAA as a proxy for overall solar output, stands at 126 solar flux units. On this date, a level that reflects sustained elevated activity well above the baseline values seen during solar minimum. The Thermosphere Climate Index, which measures the energy output of the upper atmosphere as it responds to solar heating, stands at 1687 × 10 to the 10th watts on May 11, 2026. The maximum ever recorded for this index was 49, 4 × 10 to the 10th watts, measured in October 1957. The fact that today's value is roughly a third of that historical maximum is not reassuring. It describes a thermosphere being heated by a sun that is still operating near the elevated end of its current cycle, warming the outer atmosphere in ways that increase drag on satellites in low Earth orbit, shortening their operational lifetimes and requiring constant orbital adjustments that consume propellant and reduce mission duration. Every system is connected. The warming of the thermosphere by elevated solar output affects the orbital decay rates of every satellite currently operating in low Earth orbit, which means it affects GPS precision, which means it affects the navigation systems that guide aircraft, ships, vehicles, and precision agricultural machinery, the 38 Starlink satellites. Lost to increased atmospheric drag during an October 2024 geomagnetic storm were not lost to a dramatic explosion. They were lost to orbital decay accelerated by solar heating, a slow, invisible consequence of the same mechanism that makes the auroras visible from latitudes where they are rarely seen. The aurora forecast for May 11th to May 13th, 2026 reads as follows, according to Space.com's current reporting: relatively quiet now, with a possible CME impact on May 13th that could spark activity. That is the public-facing language of the forecast. Behind it sits the CN-LIL modeling, the coronagraph imagery from SOHO, the solar wind monitors aboard Discover, and the accumulated experience of forecasters who have watched this particular cycle exceed prediction after prediction with the steady indifference of a physical system that does not have opinions about human infrastructure. Planning. Scientists choose their language carefully here. And that careful language is itself the warning. The official forecast for the next 24 hours from NOAA's Space Weather Prediction Center carries a 45% probability of M-class flares, a 5% chance of an isolated X-class event, a possible glancing CME blow on May 13th. These are not the language of a system at rest. These are the language of a monitoring network watching a sunspot region with a demonstrated history of eruption rotating steadily into the most dangerous position on the solar disk, within a solar cycle that has already produced more extreme events than models said it should. The monitoring is in place and detection is possible. But prediction is not. That sentence should be understood for exactly what it says. Forecasters can tell you that AR4436 is capable of producing an X-class flare. They cannot tell you that it will. They cannot tell you when. They cannot tell you whether the CME it might produce will be the one that travels at 1,300 km per second along a trajectory that places its maximum energy squarely on Earth's magnetosphere at the worst possible angle of magnetic field orientation. What they can tell you is that the probability of M-class activity in the next 24 hours from this region stands at 45%. They tell you this in the same tone that a structural engineer uses when they tell you that the load-bearing capacity of a bridge has a certain margin before failure, calm, precise, and entirely serious. The Carrington Event of 1859 was not predicted. The Quebec blackout of 1989 was given a warning that arrived with insufficient lead time for any protective action to be taken. Today, the lead time between a CME departure and Earth arrival averages 1 to 3 days, depending on speed. The fastest ever recorded made that crossing in 18.6 hours. The detection window afforded by Discover at the L1 point is 15 to 60 minutes before magnetospheric impact. For grid operators to implement protective measures reducing system loads, isolating vulnerable transformers, taking high-risk equipment temporarily offline, they typically require hours of warning, not minutes. The gap between the warning a CME in transit can provide and the warning that grid protection requires is not a classified secret. It is documented in the engineering literature, discussed openly by NOAA's Space Weather Prediction Center, and represents the single most consequential unsolved problem in the intersection of solar physics and infrastructure resilience. NOAA's Discover satellite is aging. Discussions of its replacement have been ongoing. The precise status of those discussions, as of May 11, 2026, is a matter that space weather policy researchers have noted publicly. Without L1 monitoring assets, the warning window does not shrink, it disappears. There is one final number that deserves to be held in the mind as this account reaches its close. The March 1989 event was classified as a 1 in 50-year geomagnetic event. The modern hydro grid, after spending $2 billion over 6 years on protective upgrades following the blackout, has been reconfigured to handle a 1 in 100-year event. The Carrington Event of 1859 is estimated to have been approximately twice as intense as the March 1989 storm by most reconstruction methodologies, placing it at or beyond the 1 in 500-year threshold on the most conservative estimates. The National Academies of Sciences 2014 estimate put the probability of a Carrington-class event in any given decade at 12%. The current decade solar cycle 25, a cycle that has already exceeded every prediction made for its intensity, is not yet finished. AR4436 rose from the eastern solar limb on the morning of May 11, 2026, and fired an M5 8-class flare that severed radio communications across an entire continent. Within 8 minutes of its departure from the Sun, it is still rotating. The system is not inactive, it is accumulating. And the geological record of every extreme solar storm that has ever struck this planet, from the telegraph fires of 1859 to the 9 hours of darkness in Quebec to the auroras seen from the tropics in May 2024, holds its evidence in scorched equipment and open archives and monitoring data that is publicly accessible to anyone who chooses to look, as a reminder that the Sun does not require our attention to continue what it has been doing for the last 4.5 billion years, and that the next Carrington-class event is not a matter of imagination. It is a matter of geometry, orbital mechanics.